Yeah, absolutely. Thank you so much, Nathan and Fatima. Like, this is I'm very honored to be speaking to you all as a part of Data Science Dojo, and this presentation is one of my favorites to give. So, yeah, I'll absolutely love to get started as soon as possible. Yeah, so I guess we're going to be starting from the very top. So, what is data science? Not in the philosophical sense, like what is, but data science is essentially the intersection of computer science, mathematics, and any type of flavor of domain. And within this intersection, um, you essentially have this jack and master of all trades of mathematics, statistics, computer programming, and a very specific and well, numerous specific knowledge areas, depending on how often you like to work on different projects and acquire different skills. So that's kind of the beauty of data science, is that your work is never really done when you're a data scientist. You're always learning. It's a very rewarding field that it's a rewarding field that likes to reward learners and people that like to research, and people that never like to stay in the same place for very long, and always like to jump around, master new skills. Now, there are many roles that are very similar to being a data scientist. There's a data analyst, machine learning engineer, and data engineers, and you all can probably think of numerous others that come to mind. But whenever I see like data science job postings, like specifically, they tend to mix up a lot of these different terms. So I guess I wanted to include them. So a data scientist is essentially somebody that uses very advanced algorithms to solve open and vague problems. So most of the time when you're a data scientist, your problem really isn't defined very well. And it's up to you. You kind of have a general idea of what you're supposed to do, but your path of getting there is very foggy. It's a journey to get there, and believe me, you're going to be correcting yourself quite a bit when you're a data scientist. Now, a data analyst, they have structured data already, and they kind of use it to solve very tangible problems that the business has. Like typically, you'll see a data analyst using tools like Excel and Tableau, and these these individuals take data that's given to them directly from their organization to acquire certain numbers and statistics that they're looking for. And then machine learning engineers, again, like this is the most common mix up that I see between data scientists and machine learning engineers. Machine learning engineers are primarily computer scientists that research and build and design the algorithms that typically data scientists use in order to solve their problems. So you can kind of think of machine learning engineers as the people that like develop the tools that data scientists usually use to solve their problems, and then data engineers are the people that construct the data that an organization needs, and they're in charge of like making sure that your data pipeline is clean, making sure that your data is clear, it's well engineered, it's maintainable, it's easy to use for different research purposes. So now, by no means are these like mutually exclusive, especially data science. Like when you're a scientist, you're going to be finding yourself pulling skills from all of these different disciplines. And likewise, a lot of the different disciplines like to incorporate skills from data science. But just so you kind of have an idea of the very subtle but important differences between these roles, I thought that it would be useful to kind of put these on the slide and lay them out for you. Now, I'll move on to the next. Actually, I'll stay on this slide, and I guess I'll ask if there are any questions on our introductory slide.
We are good for now, but we might want to wait like 5 seconds just because I know sometimes typing it out takes a minute. Does anybody have any questions about these differences or overlapping?
Ooh, we got one.
Oh yeah. Who gets to make decisions for owners?
Decisions for owners. Ooh, that's a really good question. Um, well, I guess what do you define as an owner? Like an owner of the data set, the company, in particular? Is is there like a specific definite? I hear the word owner thrown around a lot, and it's typically used to define different things. So is there like a specific like type of owner that you're referring to? Um, but to answer your question, I wouldn't say that a lot of these people particularly make the decisions. They like ooh, excellent. Somebody responded. Do
So
they define what they mean by owner?
yeah, so they're looking at who gets to someone who gets to lead someone to build the business by being the trusted advisor, either departmentally or on an
Mhm.
enterprise level.
Oh, yeah, fantastic. Yep. Thank you so much for clearing that up. Yep. So none of these people particularly get to make decisions unless you're like a data scientist owner. Again, I don't want you guys to think like these are very like structured roles with rigid lines in the sand. Like they tend to bleed into each other quite a bit. But typically, your goal as a data scientist or data analyst is to kind of create, advise, lay out objective information that based on the owner's requests that may inform their particular decisions. In terms of like design decisions, it gets a little bit different when you're in a machine learning and data engineer because those two professions are more so like software engineering where you kind of have the lead make the design based around what the request of the specific client is or what the needs particularly are. So I would say that in terms of decision making, it's not really a big part of data. Well, you make decisions in your internal field and how you want to execute the solution. But in terms of the business impact that you produce, that's primarily done by the person that you're informing. And of course, like that's not including data science owners and data analyst owners. You know, if you are tasked with making the decision in that exception, like you should definitely you use your data to do it. But yeah, I certainly hope I answered the I got to the answer that you or I answered the particular question that you were looking for.
I think you did. But let's go ahead and continue because I know we've got a lot of stuff to go through and probably not enough time to go through it. So
Yeah, certainly. So so I laid out what the data science pipeline is here, and rather than kind of laying it out on what this step is and the name of each particular step and explaining it, I thought the best way to do this is to lay out with some overarching questions that you might want to ask when you're going through the data science pipeline. So we start off with what problem are you trying to solve? So essentially to summarize that is what's the business purpose of this task that you're on or why or what particular thing is your company looking for. It's important. I'll get into more of the details and how you execute that, but that's where you want to start. And then once you identify your problem, you want to look for the data set or data sets that you're going to need, that you're going to need in order to solve that particular problem. And then you want to understand that data set. You want to understand what goes on around that data set, and you want to understand what goes on internally with that data set. Now, this is something that a lot of data scientists tend to skip is what's going on around that data set. And this is where this piece of information comes in handy because when you have that domain knowledge, you can kind of understand more about the data set than somebody that just wants to go get in there, execute an algorithm, and then leave. So that's a very important step. And then of course, what goes on internally. This is where a lot of those. Remember when I said a lot of the different definitions of data of different data professions and machine learning professions, those skills bleed into each other. And then and particularly with data analysis, this is where you need a lot of those special data analysis skills in order to execute it properly. And then the reason why we do this is to get to feature engineering and data pre-processing. So you might be asking, like, why are these two steps important? We have data, we have a machine learning algorithm, why can't we just put it into the model? Well, these two steps ensure that we are creating the best possible data for our particular model. And once we have that data, we can execute the algorithm and then determine which algorithm performs best for our particular data, and then place that into a dashboard and find the best way the user can interact with said model. Now, I don't know if we should do any questions on this particular slide, because I'll be going into each of these steps in far more detail. Should I pause for a sec, or should I just continue going?
I'd say keep going.
All right, excellent. So the problem. This is one of the most, I would say, one of the most underrated steps of data science. If you're going to solve any, if you're going to produce any value, you always have to start with what exactly is needed. And to do that, you always want to define your problem as specifically as possible. So what is the problem you want to solve, and what is the overall goal you are trying to achieve from from this solution that you're carrying out? And of course, you always want to think about, like, your what you have at your disposal, like how much data can your architecture handle, like how many which algorithms are feasible with your network. Stuff along those lines will make you be very successful. And of course, the M word. I don't know if you know, but I mastered in industrial engineering, and metrics was probably the #1 word in that entire. I've never heard a word more in my entire major, or in my entire degree. Metrics are extremely important when you want to, because it's basically, how do you quantify the goal that you're planning to solve, and it will assist you in what kind of data you're trying to look for, and exactly how you want your model to perform. So doing this will help guide your analysis so that it will be successful. And I do want to stress, I get into this in the conclusion, but you always want to be, like, iterating through your data, even after you executed your whole pipeline, to continue to improve it. So your problem will improve over time, but these are some very useful things to think about before you actually start your data science analysis. Now this is a good time for any questions, because this is a very important step that a lot of people tend to skip over, or they get a problem directly and they don't really think about it, or try to mold it into something that will be extremely specific, and it leads to a lot of very flawed analyses. So definitely, if there are any questions, certainly please feel free to ask. I'll pause for a little bit.
Yeah. We also just harp on this, defining the problem, in all of our courses. So big importance on this. So Alex, what are some of the steps that you take in defining a problem?
That's certainly that's an excellent question. So the first thing that I do when somebody asks me for something is, I always ask, what is your essential goal to this? By understanding the goal, you can kind of guide the rest of the questions in order to get to the proper analyses. And then from that goal, I start asking about metrics. In particular, how do they want, what are they trying to, or how do they want to measure their particular solution, or how do they want to measure the success of their particular solution? And then from their metrics, you always want to understand what kind of solution they're looking for. Like, particularly with data science, you always want to understand whether they want performance or analytical capabilities. Because if for example, if their problem is, we want to know the top contributing factors to heart disease, then you're going to want to use less expensive, less computationally advanced algorithms that provide a level of transparency that can give your audience or your client the best possible analytical capabilities by allowing them to peer into how your model makes particular decisions. However, if your client would say, hey, we want to have a model that's the best at predicting heart disease, and we don't really care about analytical capabilities, then you may want to go with something a little bit more computationally expensive and black box compared to the more transparent algorithms. So, something like neural networks or gradient boosting, or not non-linear gradient boosting. And then of course, you always want to understand the constraints that you're working within, particularly if the client, because the constraints that the client desires will definitely shape your solution in the long run. Like if they don't have very much computational power that they're working with, and they can't get anymore, it's important to say, hey, we want to use a less computational expensive algorithm that's very scalable. Maybe something like a neural network wouldn't be suitable in that particular instance. We might want to go with something like logistic regression, or if logistic regression in order to solve that particular problem. So that's kind of how I like to lay out different lay out the problem in order to start my analysis. But the big thing is, but again, like the M word, metrics is a huge thing. Like how do they want their, like what is their goal and how do they want it measured is the very first thing I'd like to get to the core of before I start going into anything else.
And speaking of metrics, we had two questions coming about metrics. They're pretty much the same, so I'm just going to ask one of them.
Yep.
So there are so many metrics based on the data set balanced or imbalanced. Do you have any suggestions?
That is fantastic. I don't want to spoil it, but I have tons and tons of, but believe me, I have tons and tons of solutions for getting into data set imbalance. So I don't know if I should answer that now, but it's a big part of the presentation later.
Okay, so maybe we'll pause on that one. And then there's one person that it's not necessarily a question, but just wants to emphasize that metrics are important, and they can say that they have experience in this case and they've worked with unbalanced data and used accuracy as a metric, but quickly found out it wasn't a good choice and switched to precision and F1 score. So, and I'm sure you'll probably touch on those maybe later.
Yep, I'll go into different ways you can evaluate your model, but yeah, very, very good questions and very good questions and comments.
Okay, and then last question, Patrick, you've got the last question for this section so that we can move on after this. Have you run into any clients where they don't have standard or commonly accepted definitions on their metrics? What are some of your successful strategies in overcoming these challenges?
Oh, all the time. Well, yeah, definitely. You will run into clients that don't really have a good handle on their metrics. A big thing that you want to get at is, my big suggestion is to ask questions. And when you learn how to ask the right questions, you can essentially get an idea of what your client wants before they have an idea of their metrics. So I guess if you want to make like a churn model, and somebody is saying, oh, we just want to see how many people leave. Well, if your goal is to get an idea of our retention, you kind of want to dive deeper and say, oh, we don't want to just see how many people leave, we want to see how many people quit. But if you kind of massage the client with those questions, you'll eventually be able to finesse your way into getting their desired metrics without even them having an understanding of it. So yeah, to answer your question, long story short, questions. That I couldn't recommend that enough. Like questions and communication.
Okay, so let's continue on, and
Yep.
We'll pause again when we have more.
Yep. So once you have the specific problem that you're trying to solve, with that problem in mind, you want to start looking for some data. Now, I posted in this slide, I posted a lot of links that you can use to find different data sets on different on different websites. Kaggle, data.gov, Driven Data, UC Irvine, Google Public Data Explorer. Now Kaggle is it's well known as like a data science competition site, but it's a really, really good data repository. And then data.gov is also excellent for a lot of government data sets. And same with Driven Data. Driven Data is a lot like Kaggle, but a little bit smaller and restricted, less daunting compared to Kaggle. It's another great place to find data. And then I like the UC Irvine machine learning repository for when you're practicing. But I guess while it does have good data sets, a lot of them are a little bit too nice and clean. It's good to start out with, but when you want to really start owning your data science skills, those data sets they're good for testing algorithms that you make. Like if you want to learn like if you see this deep learning algorithm that you really want to get into, it's good for that, for testing stuff like that. Or if you want to learn a new architecture like PyTorch or something, then it's good for testing that stuff. But in terms of like actually producing projects and finding particular data, you may find a gem there, but particularly it's not what I recommend as like your primary source, because a lot of it's just too small, it's too small and restricted. But again, if you could find something you need on this, so that's why I decided to include it. And then Google Public Data Explorer as well. Excuse me. Now, there are sites that specialize in data for a particular domain. Like the UN is a fantastic repository if you want to do like a project on human rights around the world. There's like the global health repository if you want anything involving like hospital data or hospital data. I remember the UN also has like a economic factors for like poverty. So it's worth it. It's worth doing some of your own digging to see if there's a specific repository that fits your problem more specifically than the rest of these. But again, if you want to start your project and you need some data, for your portfolio, like these are some fantastic places to start with. Especially Kaggle. Kaggle is one of my favorites because they have a lot of raw and rough data sets that you can get into that'll really push your data science skills to the limit. So I like Kaggle a lot, and they're typically a lot of them are very easy to download. Yep. And I see we do have some questions. I'll take a pause for any questions right now.
Okay, and I just want to say that the questions I'm seeing, I think we could probably save to the end because they're not relevant to that specific slide. So I would say let's continue, and we'll get to them.
Yep, definitely. So let me move this real quick. So I'm gonna go. I have kind of like a dense slide here. So when you're getting your data together, I kind of wanted to make some data engineering tips that a lot of data scientists need to keep in mind when you're finding your data, because they might come in handy. Now, again, I want to emphasize this enough. Those different roles, there's no strict line. There's no stringent separation between them. A lot of the skills blend together. Now I'll go into the data analysis later, but this is some of the data engineering tips that you're going to need. So the first thing when you look at a data set is you always want to keep in mind what is the primary key of that data set. Now, the primary key, you can kind of think of it as a unique identifier for each individual row in that data set. So for example, you have a row of CDs. Say you have CDs and artists, like the example here. Oh, excuse me, sorry. the CDs, the ID of CDs will be the primary key for the CD data set. So, and then from the primary key, a data set might also have foreign keys. Now, what a foreign key is essentially an identifier for a different entity within the same data set. And this identifier may be the primary key of a different data set. So a good example is, again, going back to the CDs, you have a CD data set, you have the CD ID for each individual CD within that data set, and then you have the artist ID within your data set. Now, or within your CD data set. Now, the artist ID is an entity in and of itself. And if there's an artist data set, that artist ID will be the primary key of the artist data set. Now, this is important because if you want to have more than one data set, that you might be wondering, why am I talking about these concepts? Well, if you want to make a model with more than one data set, it's important to keep these in mind. Like, you always want to think about, how can one data set connect to another data set if I want to put multiple data sets within my model. Now, once you find those keys and know how to connect data sets, you're going to want to think about the type of relationship that they have. So essentially, actually, before that, you kind of want to conceptualize what kind of joins you want. So essentially, there are four different types of joins. There's the inner join, which is essentially you connect data based on so basically these joins are based on what's present in both of the data sets. And the inner join is what is present in both data sets are the only ones that are kept. And so essentially, going back to our artist CD example, the inner join would be every single artist in the CD set every single artist in the CD set and every single artist in the artist set are only considered and placed in the final product. Now, when you go to something like a left and right join, I call it like a one-sided join. This is different because in one particular data set, you may have a case where you want to keep all the entities within one data set, but you don't really care about the entities and the dropping entities in a different data set. So say you want to have a model you want to create a model based on CDs, and artist is just kind of an attribute that's nice to have, but it's not a necessity to include. You can use a left join where you keep every single CD in your CD set, even CDs that aren't in the artist set, and the artists in the artist set that aren't in the CD set are dropped. And the final one is the full join, which is all artists and CDs are kept within your data set. Now, full join is when you want as much data as possible, but it can get pretty messy. I personally have never used the full join. Typically, a lot of the joins I use are either left joins or inner joins. But full join is essentially where you just keep all of your data on the join, whether they're a part of the different data set or not. Now, again, with joining, you want to consider the relationships that different attributes have. And essentially with relationships, you have one-to-one, one-to-many, and many-to-many. So you can kind of consider this as, for example, say this is a good one here, car company and the car model. A car company will only produce one unique car model, and one unique car model only belongs to one unique car company. That's how you can kind of think of that. And then the one-to-many, the doctor and patient. So one doctor has, well, that's not particularly the best example, but just in a world where each patient has one particular doctor, so one doctor has many patients that are associated with it. However, each patient only goes to one particular doctor. That's how you can kind of think. That's how you can kind of think of like the one-to-many. And then for the many-to-many, you have students and subjects. So you have students taking many different subjects, and subjects related to many different students. Now, this is the kind of relationship that you need to watch out for, because this relationship essentially creates vagueness within your relationships and can be problematic when you're trying to join a set. So when you have this many-to-many relationship, you might want to consider some kind of method to create that unique relationship. A lot of people like to use something called junctions, where they essentially create many to one relationship to the junction table, and then a many to one from the other side. So they essentially create two one-to-many relationships rather than just having that many-to-many. But yeah, the many-to-many relationship is something you're going to want to watch out for going into this. Now, going back to our example, if we want to identify the relationship, this is an example of a one-to-many in the most clean sense. Like, there are in the most clean sense, this is an example of one-to-many. A particular artist is going to produce many different CDs, right? But a CD will only be associated with one artist. Of course, like, this is in our hypothetical world. Now, you might get clever and say, oh, well, there are many instances like Justin Bieber featuring Nicki Minaj, in some instances where multiple artists are associated with a particular album, but in that case, it's still like one artist is credited for creating that particular album, and then that album is only credited to that one artist. So it's the one. So in our albums and artists example, it's a one-to-many relationship where artist is one and then many albums. Yeah, sorry, you guys probably have a lot of questions. That was a lot to cover in one slide. So yeah, I'll pause for a little bit. Ask, is there any confusion?
Yeah, let's give it a second, because I'm sure somebody has a question. Maybe while we wait, we can answer one of the questions we were going to save for the end.
Yep.
This comes from Jorge. If you know business knowledge, what are the main steps to prepare your data before building the model?
Yep. Man, you guys love to I love how eager everybody is. That's another fantastic question. I will get into that later in the presentation, but that is a fantastic question.
Okay, I haven't seen any questions come in yet, so maybe there's one. So this person knows it's pretty basic, but just wants a reminder about what you mean when you say key.
Oh, yep. Certain. Yep. Good question. Yeah. To emphasize this, a key is essentially an identifier for a particular entity. So you can kind of think of it as how each row within a data set is identified. And the main purpose of the key is to the main purpose of that identity is to construct your data set in a way where it's intuitive how each table connects with each other. Now, you might be asking yourself, like, why shouldn't all the data just be clustered together into one giant blob then, and then just stored? Well, the main reason why, so you can kind of think of a database as a collection of numerous different tables that each store information. And the reason why a database is structured like that is for efficiency's sake. As I said before, like, an artist can produce many different CDs, right? But we aren't going to be in the situation where, but if we didn't separate each artist or each piece of data into tables, we're going to be repeating the artist information as many times as they have a CD, which is a huge waste of space. So functionally, keys serve as that identification for identification within each data set, and they help connect data together through that identification. I know I went into like a little bit more in depth, but typically I like to understand like why we do certain things when whenever I hear an answer to a question. But yeah, that is a really good question for some very important emphasis.
Yep, and the person that asked that says thank you. That was very helpful. So I think we can continue, and then again we'll stop again when we have questions.
Yep, definitely. So now context, the big C word. So this is where so domain knowledge does come in handy when we go to the internal analysis or data exploration. But this is where our domain knowledge really does a lot of contributions to our project. Now, with proper context, it'll give you knowledge. It's like you're almost you understand everything that's going around your data set and why your data set is the way it is, and what each feature means within your data set. Now, this knowledge can contribute very heavily to feature engineering, and and has the potential for creating some very potent features when you actually create your data set. Like it can also give you a good idea of what additional data sets you would like to add to your particular data set in order to provide the best possible solution to your problem. So here's some questions you can ask to gain like an example of context. When was the data collected? Like what was going on when the data was collected? Why was it collected? What were the limitations? Like this stuff can be pretty helpful. Where was it acquired? This could potentially this can potentially shine a light on different biases that might be present within your data and who it was acquired by. Excuse me, I'm so sorry. Who it was acquired by might also be a very useful piece of information so that you can avoid different biases when you start to produce your model. And it can also provide you with information. And by understanding where it was acquired, you may want to do some research on the area in which it was acquired and the people that it was acquired from. Like that could also provide some additional features that could contribute to your model. What are the basics about your subject? Like if you have an investing data set, or if you have like a housing price data set, that's a good example. You may want to do some prior research on real estate, like how houses are valued. How does area potentially affect housing price? How does area affect housing price? What the demographic makeup of said area in terms of like age, how that can affect different housing prices. So by doing that, and by like getting in the shoes of what a real estate agent is, by getting in the shoes of information commonly known to different real estate agents, like that could bolster your analysis quite a bit in your project. It can give you an idea of different how to efficiently engineer features. Like maybe it's commonly known that in areas possibly 65 and older, the houses tend to be cheaper because a lot of young people don't want to move there. So instead of going with the shotgun approach of just having different age groups, you may want to separate into age demographic 65 plus or age demographic lower than 65 plus. Stuff like that can be very useful. What do the columns mean? Like this is very important. You want to understand what each of your columns mean. Like if you have a column that's just TFID, you're going to be like, man, I have no idea that's just the random acronym I pulled out of my head. But if you have just a random acronym as a column, you're going to want to do research into that. Like what is the real world example of TFID? What is it actually like? How can I picture TFID in my head? Like how is TFID usually quantified? What is a good TFID? What is a bad TFID? Stuff like that can really help you. And of course, what is a logical value for each column? Now, this is very important for cleaning data especially locating outliers. Sometimes you can, people like to have a shotgun approach when they identify outliers, but sometimes logic, simple logic can be very useful. Like a good example is if you're in an old folks home and there's you're in an old folks home, and if somebody in the old folks home is like 30, has an age of 35, something's not exactly right there, because that typically people around the age of 35 aren't don't live in an old folks home, or a senior living facility, I should say, for like, as a more politically correct term. But but those are some things that you can potentially do in order to increase the potency of your model. Now, again, this is nowhere near the end. There are hundreds of thousands of questions you can ask, but this is a good starting point to kind of get an idea of what you want to look for when you start, before you even start exploring your data, like what kind of additional research you want to do before you actually get into your analysis. Now, I know that tons of people have questions on this one. I already see them rolling in. I'll definitely pause for those.
Yeah, I've tried to answer a couple of them to minimize, but so one person wants to know, like, how do they know which visualization to put on a report if they don't work or have really any domain knowledge within a specific industry?
So there are some graphs that are meant to display certain data. Like, for example, if you want to display a distribution, typically you'll go with a histogram. Like, typically you want to display distribution if you want to generally see the layout of one continuous variable. If you want to look at the distribution of categorical data, like a bar graph will typically be useful. If you want to see the interaction between two categorical features, a stacked bar graph might provide that specific information. If you want to see the relationship between two different continuous variables, a scatter plot will be extremely useful for that. And then I guess if you want to kind of see the interactions between categorical variables and continuous variables, maybe some type of scatter chart with differently shaped dots. You always want to be careful of the amount of data you display on one graph at a particular time, but a scatter chart with different types of dots, maybe some type of distribution plot with some type of coloring on it that might indicate certain values. But yep, but yeah, basically, to answer the long story short of your question is, look at the data types that you want to plot in your particular graph. And by understanding which data types you really want to look at, there's a general graph that is optimal for displaying said data type. And it's up to you to kind of make that graph as readable and useful as possible. And I guess another piece of advice for like data visualization is restraint goes a long way with data visualization. You'd never want to overwhelm your user with too much information at once. For that means that they might get lost in what you're trying to display. So always make sure you have a point. Use the right graph for a particular type of data that you would like to plot, and make sure that you use restraint when displaying the data to your client.
Perfect. And I'll get one more question in before we move on. And I think it might have been answered in the chat, but if one person asks it, that means there's probably more people that have the same question. So they just want you to go over the many again.
Oh yeah, of course. So yeah, sorry, I went through this really quickly, but a many to many relationship is essentially when you have numerous different entities that relate back to numerous different entities. So in this example, it is a student and subject. So you have many, say you're in a high school, right? You have many different students taking biology 101, right? Or you have many different students taking biology 101. And then biology 101 has many different students associated with that. So as a result, if you were to look at biology 101 in like a table, you would see different people. You would see biology 101 being able to be related to numerous different. You would see biology 101 in the subject table being able to be related to many different students. And then at the same time, you would see biology, and you see in the student table, many students taking biology 101. So essentially, the reason why this is problematic is if you try to join those sets, you don't really understand the relationship between student. You don't really understand the relationship between student and subject, right? Because a subject can be related to many different students, and many different students can be related to many different subjects. So as a result, you don't really have a unique attribute for each student within a particular subject. You just have a general idea of their relationship. And in student and subject, maybe you can kind of get away with it depending on what kind of model you're doing. But many-to-many relationships are problematic when you start to get into more specific things where different relationships have to be very well defined in order for the problem to properly be addressed. Now, a way to handle this is what's called a junction table. Now, what a junction table does is it's a relationship table that relates the IDs to each other. And essentially, this junction table creates a many-to-one relationship with the opposing data set. So by creating this junction relationship table, you essentially boil down this many-to-many relationship and give these tables the ability to connect, create two one-to-many relationships. I think we're quickly running out of time, so I heavily encourage you to look up junction tables and many-to-many relationships. It's very important, but I hope that I got the point across. Are we good to go on, or
Oh yeah, sorry, keep going.
Yep, definitely. I hope that I answered the questions sufficiently. But now we get into exploration. Now, the difference, oops, sorry, skipping ahead a little bit. The difference between exploration and context is that exploration is primarily the internal knowledge from your data set. So this type of information is what's derived from the data itself, like going into the graphing before, like, do we have a relationship? Is there a potential relationship between the price of the house and the number of bathrooms? Is there a relationship between the number of bathrooms and number of bedrooms? How does that affect the pricing of the house? How does the state affect the prices? Like, all this stuff can be found within the exploration. Now, you might want to ask yourself, like, what are the categories for the different fields that you have, and what are those category frequencies? Going back to the beginning when somebody asked about imbalance in your data set and how we deal with that, like, are there imbalances that we have to think about? Is, like, if we're looking at a fraud data set for a bank, there are numerous different there are so many different so many more sorry there are far more entries within that data set that are legitimate, and then there are far less that are there are far less that are fraudulent. So how that we can find that issue. We can also find if there are any confounding variables. This isn't with structured data, but a very famous case of a confounding variable. So a confounding variable is essentially when you have a variable that's when essentially a variable takes over and drives your model's result that's contradictory to what you're looking for. So a fantastic example is the husky versus wolf machine learning experiment. So in the husky versus wolf experiment, I think it was you might want to check me on this. I forget which school it was, but a machine learning or a computer science department at a particular school was able to make an image processing model that can tell the difference between a husky and a wolf with 99% accuracy. Now, the reason why it could do that was the background for the huskies were all grass, and the background for the wolves were all were all snow. So as a result, it wasn't really telling the difference between a husky and a wolf in that situation. It was telling the difference between between grass and snow. That's what's called a confounding variable, because that variable that they didn't intend to drive the analysis was driving the analysis, or was driving the model predictions. So if you had a husky in a grassy, or a wolf in a grassy area, or a husky in the, actually more logically, husky in the snow, which is pretty common, it wouldn't be able to identify the husky in the snow. It would just say that husky in the snow is a wolf because it's in the snow. It's basically a confounding variable is an input within your model that your model makes false assumptions on, and can drive very problematic predictions, and that's definitely something to look out for. It's a lot like if you have yeah, I'll just move on. Sorry. But yeah, the husky versus wolf is a pretty good example. But yeah, you might want to look at the relationship between your fields. From this, you can find out if different fields are redundant, if some potential relationships could more powerfully drive your solution, and you might want to look at the different field distributions. Now, with all this information, you can also find out what in your model, like which of your features have the highest ability to perform predictions, but you can also kind of see how your features can potentially fit together to produce a better result. Like it goes along with that context slide in order to optimize your potential pre-processing and feature engineering, and bring that to the maximum, and make sure that you have the best model. Yep. Any questions for the exploration portion?
I am not seeing any, but I'm sure there is.
Yeah.
But I know, Alex, we're almost at the 60-minute mark. So I just want to
Yeah.
make sure you're good to continue. I know yesterday when we were in our little meeting about today, we talked about, potentially going longer. So I just want to make sure you're good to go. Otherwise, I mean, I'm happy to be the bad guy, but
Yeah, definitely. I'm definitely still good to go. I'll try to get through the PowerPoint because I still have code that I want to review, but my goal is to definitely get through the PowerPoint, and I put a lot of effort into like commenting and sectioning off the code. So I'm hoping that it'll be easy for people to walk through the executions of said code after. Certainly if we don't get to make it then, but yep.
Yeah,
So
friend Patrick is good to go for another 30 minutes. So
okay, excellent.
But we have one question. I'm not sure how you'll answer it though. So this person wants you to talk more about feature engineering.
Yep, we are right there.
Okay.
Excellent question. Definitely. Yep. So my answer is yep, I will definitely talk about feature engineering, and we are there right now.
Maybe,
So
maybe I can
sorry.
make one comment. Some people do have to go.
Yep.
So there will be a recording of this. You can find it on Data Science Dojo's YouTube channel, or on our website, datasciencedojo.com I think it's /events. So yeah, we've got a lot more to cover, but there will be a recording. So don't feel bad if you have to drop off. You're not going to hurt our feelings. We're happy to have you here, and it will be recorded. So, okay, Alex, there you go.
Certainly. So, yep. Thank you. Thank you for that comment or that question about feature engineering. I would consider this the most pivotal step in all of data science. Other than the problem, of course, I would consider this the second most important step, because this is where you really get to, this is where you make the 30-40% accuracy gains versus the 1 to 2% you get from optimization. So so thankfully, the reason why we've been gathering this information, like you might want to ask, why did I spend so much time talking about context and internal exploration? Well, it's because with this knowledge that we've acquired from the previous two, we can start getting into feature engineering and building our own fields that our model can use. So here are some ways you can think about feature engineering and some questions you can ask based on the information gathered. So can we combine columns to make something more useful? So if you have two different columns whose information isn't that useful by itself, but if you combine them, it can provide a very potent variable that might be extremely useful in your analysis. As an example, when I was doing my own project on a fraud data set, I found out that the beginning and ending balances for the beginning and ending balances for a transaction weren't that useful on their own. But when I combined them, there were very strong indicators from the delta between those two that can indicate that was an extremely useful indicator for fraudulent analysis. For example, if the transaction was 0, it was always classified as fraudulent. And if the transaction was as much as the person's bank account information, or as much as the if the delta was equal to the person's bank account, or if the delta was equal to the person's bank account value, then that was also an indicator of that was also a surefire indicator of fraudulent transactions. So combining columns is something that you can do for feature engineering. It's very useful. Converting field types. Say, for example, like I said previously, if you're a real estate agent and you know that the average age in an area is like 65, that you might want to take out average age for a particular household, and aggregate the ages in that particular area, find an average age, and then produce a Boolean variable for produce a Boolean variable for average age for a particular area. And that can prove to be far more useful than just simple average age of a housing area. So in that case, we're converting from int to a Boolean, but you might that might not be granular enough. So you might want to consider age groups. Like this neighborhood is typically 20 to 30. This neighborhood is typically 40 to 50. This is 60 to 70. So using those age groups instead of particular age might prove to be useful, because they represent the different stages in a certain person's life. And as a result, at different stages in your life, you might want to live at different places. So that might be more useful than just the simple Boolean feature. But converting the fields is also pretty valuable. Incorporate different information from a different data set. Remember the data engineering slide that I went over before. Can you grab different data sets from all over the internet? Like if you have a housing data set, can you grab a geographic location data set? Like can you grab a city data set? is there information about the particular city that you're living in that might be potentially useful? Like for example, how many restaurants there are around in your city, museums in your city, general like cost of price of living, average salary in your area, like that, all that information. Those are engineered features that you gathered from a totally different data set, and it could provide a lot of useful analysis in your, or a lot of useful features in your model. Um, change the values with outside scripts. Sometimes external data or external scripts can provide good pre-processing. When I wrote this in my head, I was thinking of the way Google Maps does. Google Maps is able to derive a location from latitude and longitude. That can be useful. You can find a way to use the Google Maps API to generate that, to generate those locations if you have a latitude and longitude, and then you have you have a ton of different information in your data set that you can potentially use as your analysis or related to a different data set. And of course, how do our new something you want to do at the end is how do our new features relate to the rest of the field? Going back to the Delta example, I was able to find out that in every single instance that that a person's bank account was completely cleared out by a transaction, or there wasn't any change at all, those are all fraudulent. Those are all fraudulent transactions. Those are all fraudulent transactions 100% of the time in that scenario. So you might want to consider, you might want to take a look at, once you engineer those features, how you might want to do some additional data exploration with the rest of them. And again, the theme of this pipeline is that it's not a standard procedure where you finish one step and move on to the next. It's fluid. You want to, if you do your data exploration, your context, your data exploration, your feature engineering, you might want to go back to more data exploration. So yep, it's certainly very flexible.
Okay.
Yeah, any question? Oh, sorry.
Yeah, I was gonna say we do have a quick question. And it's another well, it'll probably be a fairly basic question. When you say fields, are those equal to variables, or do they mean something different?
Nope, they're equal to variables. I'm horribly sorry for not clearing myself up, but that is a very good question, and I should have been more clear about that. Yes, they're equal to different variables or attributes of a model. You can kind of think of fields as the columns for your data set in a structured data.
Okay, and I'm not seeing. We have a couple comments, but I wouldn't call them questions. So
okay,
I think we're good to continue.
Yep. I hope it's nothing mean.
No, only good things.
Okay, good. But yep, now for some pre-processing. So we're not necessarily done. Before we put our data into a model, we do need to have some additional steps. I know, like, we all want to get to the modeling, but we just need to do one more thing, and that is we want to. These are some suggestions you can go through to get your data ship shape for your modeling. So you might want to. Some models, particularly linear models, have an assumption that all of your features are normally distributed. So there are certain algorithms that you can incorporate, or transformations you can incorporate on your data in order to make it go from non-normally distributed to normally distributed. Specifically, the exponential transform and the Box-Cox, or exponential, logarithmic, and Box-Cox transforms. Those are all very useful for changing your model's distribution. It essentially puts your model on a different scale, so that the distribution goes from exponentially distributed, or it goes from a distribution that may be like a little bit imbalanced to more of a bell curve. Now, will your model be better on an aggregated set or a non-aggregated set? So what I mean by that is, say you have, say your only set is based on CDs, but you want to predict whether an artist will be successful or not based on based on income or salary. you take your CD set and you can essentially make it so each line of that CD set is an artist, and you take your CDs and you can use those for different feature. Like you have an artist on your artisan. Every row is defined by an artist, and you have number of CDs, and then maybe you can take a sum of how much each CD made when it, or the total number of CDs sold when they sold to the public for each particular artist, stuff like that. This is the group by method in pandas, in case you're wondering. And then we need to encode our data. Now this is the more like techie part of this slide. So encoding is essentially, there are two types of encoding. It's essentially turning categorical features into numbers. You can think of it like that. There's label encoding, and then there's one-hot encoding. So a label encoding is, say for example, you have you have students and subjects, right? And essentially, or you have students and how about the students and like grade levels? You have freshman, sophomore, junior, and senior, right? To encode it, you can say you put it in a label encoder, and essentially you turn freshman, sophomore, senior, junior, senior into 1, 2, 3, 4. That's for label encoder. Now for one hot encoder, say you have that same example, students are freshman, sophomore, junior, senior. You will essentially create a data set where each different category is its own column, and it essentially turns that different column into a true or false value versus for a particular student that has that particular attribute. So say, for example, a particular student is a freshman, you'll have a freshman column here, and then that will be categorized as true. And if a student is a sophomore, in the freshman column, that'll be categorized as false. But if in our hypothetical sophomore column, that'll be categorized as true. In this particular example, you have apple, chicken, broccoli. For the label encoding, it's 1, 2, 3. And then for the one hot encoding, you have apple is true, apple is true. For chicken and broccoli, these are false. And then for chicken is true. And then for apple and broccoli, these are false. And then from there, you're going to want to drop columns to avoid overfitting. I'll talk more about overfitting in the evaluation section, but essentially overfitting is when your model is so overtrained that it doesn't produce proper predictions in the when you put it into production. So for this, you can use different reduction techniques like principal component analysis and step model elimination, or just drop what you consider redundant features from your internal analysis or your data exploration. So so yeah, I would dive more deeply into principal component analysis, but we don't really have. I'm running very short on time. So do we have any particular questions?
I am not seeing any. So, and I'm not going to say let's pause. I'm going to say let's just continue. And then if questions do come in, we'll just make sure to give an answer at the end.
Yep. So guys, we made it. This is what we've all been waiting for. Finally, we can get to the machine learning model, or to the modeling portion. And you're going to be very disappointed, but it's only one slide, and we have our evaluation afterwards. So essentially what machine learning is you have various algorithms that create a prediction based on a certain number of inputs. And then from that prediction, it uses that error to adjust itself in some way, and then repeats that process until the various parameters, or until the various adjustments aren't really changing in your model. And from there, it decides that it has the optimal model, and then uses that as the to end the training. So basically, here are some examples of different machine learning algorithms that you can use. There's logistic regression. So logistic regression is your linear model that with numerous different coefficients that are fit on different numerous coefficients that are fit and optimized until you have the best predictor until you have the best predictor where you put a certain number of features in and you have an outcome. Logistic regression / linear modeling is the most basic of the machine learning, but it's very important, especially for transparency. And then you have decision tree, where essentially the model finds the best optimal splits for each particular field and then creates a tree. From these splits, it creates a tree that it will produce predictions from. Now, and then we have random forests, which is essentially an ensemble of different decision trees. So essentially what this does is it creates a decision tree from a certain subsection of your data. And then once it creates that tree, it creates another one and another one. And then all the trees that it creates are aggregated together. And then a prediction is made based on that. And then you have boosting, which is slightly different from random forest. It's similar but different, where you do have these bootstrap submodels. I say usually trees because there are boosting methods that are not tree-based, which was exciting to discover. But there are boosting methods that aren't tree-based. And essentially, boosting methods are an example of this ensemble model where it starts off with a weak learner, but each tree or each submodel, which in this case tree, each tree within that model improves its own predictions based on the error of the previous one. And then all of a sudden you have, so your trees improve, and then you have the voting at the end, or the aggregation at the end that produces the aggregation at the end that produces an output. And then you have support vector machines where data is placed on a given hyperplane, and essentially you create this function that separates data on said hyperplane in order to create those predictions. Yep, and that was a lot to dive into. Are there any questions? This is I can literally have an hour-long talk for each of these, maybe even more.
We're gonna have to schedule you for a whole series.
Yeah, definitely. I'm telling you, there's so much to get into with each of these different algorithms. But it was the most difficult part of this whole presentation was summarizing these into one sentence for each.
Yeah, that's fine. So one question is, what would be a simpler way to check redundancies? After combining columns, the old ones usually are dropped. I didn't say that like it was a question, but that was a question. So
yeah. So yep. So I guess one thing you can always check for redundancy is you can first use the context to first find redundancy. Like if you have address and street, right? Like the street is a part of the address, so maybe you don't really need street in there. So if you want to quickly drop stuff, you can kind of use your intuition that you acquired in your context stage in order to understand at a glance like what to drop. Now, in terms of, is there like a programmatic way to drop redundant columns, you can always consider stuff like principal component analysis, which will identify which columns don't really have that much of an impact on the variance of your data set. And that can certainly be a very programmatic way of dropping columns, but it's important to combine that with your information. Again, what a lot of people have trouble with when they go into data science is they consider it a very like robotic process when it's not. Like data science involves a lot of human input in every single step of the way. Maybe except for other than the machine learning step, it involves a lot of human input. So of course you want to oversee to make sure that it's what you want to do. But yeah, I hope I answered the question sufficiently.
I think so. And so let's continue on and
Yep. We're almost done with the PowerPoint. So so now we have optimization. Now essentially you want to get So once you're done modeling, you want to squeeze the last bits of accuracy or other metrics from the model. Grid searching is essentially you take parameters and put them on an X and Y axis and test your model with different parameters that you laid out over and over again until you find the model with the best metric that you're looking for via these parameters. Now, grid searching, if you're a computer scientist and you're in here, you might be thinking to yourself, man, that is inefficient. You might be cringing to yourself looking at this and saying, man, n squared complexity, that's not, or n squared complexity, this is not ideal. And you're right, a lot of other computer scientists felt the same way. So they invented different types of parameter optimization algorithms, like random optimization, where they gather a random subset of the different grid of this grid, and they only test the model with a random subset of parameters in order to get the best one. And then you also have Bayesian, which is a similar process. But I recommend looking into this. Like it'll certainly help a lot with your modeling. But yeah, grid searching, it's very useful for squeezing the last drops of accuracy from your model, but it can be very inefficient. So it's important to understand different methods to reduce that time complexity. Yep. And then for evaluation and validation, now we get into, I remember somebody previously when we were talking about the metrics said, hey, our metrics changed. I thought accuracy would be the best, but then I realized that precision and recall or F1 score were the best. But this is where you also want to see how your model is performing. So the first thing you want to check for is, like, you want to make sure you didn't overfit or underfit. This is a great graphic for overfitting and underfitting. So essentially, overfitting is when your model is overtrained and it performs well on your training data, but when you try to put it in production or put your model in the real world, it doesn't perform very well. And then underfitting is where you don't train your model enough. You don't train your model enough, and it produces inaccurate predictions in your training stage and your validation stage. So it's important to kind of test for both of these, and I'll go into different ways. So to test for underfitting during your training phase, there are lots of different metrics you can use. You can use accuracy, precision, recall, F1 score, and ROC curve. So precision is essentially, I believe precision is out of the total number of truths, how many of your truths were correct. And in recall, it's out of the total number of, I believe it's false positives. And so precision is true positives over true positives plus false positives. So it's saying, like, how many times after you said something was true, did something turn out to be true? And then recall, it's kind of looking back. It is true positive, if I remember correctly, it's true positives over true positives plus false negatives. So out of the total number that were correct, like, how many did you get right? So you can kind of think of recall as looking back and evaluating with hindsight. And precision is how many times when you said something was true, was it true? And then you have ROC curves, which essentially, like a graph, I believe, comparing true positives to false positives, and F1 score is a score relating precision to recall, and combining those two to create a better metric than accuracy. And then accuracy is how many did you get right versus how many there were total. Now, once you get that, you can I can go into different methods of testing overfitting. So one method is called cross-validation, where essentially you have you split your data into testing and training sets, and you pick one piece you split your data into different pieces, and one piece is designated as your test set. The rest of the pieces are designated as your training set. And for each piece, you iterate your model to test on the testing and training sets, and you switch out which piece is your testing set versus the rest that are your training sets. and then you find the average of that error at the end. So this is a good visual representation of it. You see, this is an across 5 cross validation. You see 1/5 is designated as the testing set, 4/5 are the training set, and you iterate through those until all different pieces had a chance to be the testing set, and then you find the average error of that. And then another thing you can do is set a piece of your data aside before you even start cross-validating in order to have a different in order to have foreign data that wasn't even a part of your the training process at all, and use that to evaluate your model just to see how your model performs with data that's completely foreign to it. So those are some good methods to reduce overfitting, and then to reduce underfitting, it's important to check each of those different metrics. Yep. And then finally, any questions on this? I guess I can I'll just move on. Then you have dashboarding, which essentially what you want to do is you want to pickle your model. It's a method that can save your fitted model, and you can transport it over to your dashboard. And and the reason why you want a dashboard is it can definitely give your data science portfolio an edge, because you didn't just start at the machine learning part. Like, you learned how to deploy your machine learning part on a different server, or you can learn how to do different unique ways of deploying your machine learning model. Now, this is very useful for portfolios. It can be very impressive to show that, hey, not only can I train stuff, but I can deploy it as well. And in order to model this, you might want to ask, how much detail do I want when I want to make this dashboard? What do I need to add to it? What is the best way somebody can interact with my model? Some libraries that I recommend: Flask, Streamlit, and Dash. Flask is if you have all the time in the world, but you want to have very strict control over the specific areas of your dashboard. Flask is very useful. It's a very in-depth. Dash is kind of that midpoint between Flask and Streamlit, where you have where it's more streamlined, but it's a little bit more difficult than Streamlit. Streamlit is that very fast, quick dashboarding that can be extremely effective. And if you're strapped for time for your dashboard, like, Streamlit can definitely be very useful for that. And if you don't have really any specifics for how you want your, if you don't really have any specifics for how you want your dashboard laid out, like, Streamlit is very useful. Also, out of all these, Streamlit's definitely the only one where you don't really need a lot of HTML, or you don't need a lot of HTML knowledge to execute. The syntax of Streamlit is very much like typical Python. I mean, Flask and Dash are implemented in Python, but they involve a lot of HTML as well, HTML code and CSS. Flask specifically is very HTML heavy in order to design your whole front end. And Streamlit is you only need Python, and it's the syntax is very Python oriented. Basically, your widgets or the buttons on your dashboard feed directly into a variable, and then that variable can be put into a model. Yep. And then we're at our conclusion. So yeah. So in this talk, we kind of went over these general steps for the data science pipeline. Now, I do want to emphasize that this is not a structured ladder at all. It's a very fluid process. It's just a general thing that you want to go through on your first time, but for example, if you're on the pre-processing step, you might want to go back to exploration, and then go to feature engineering, and then maybe you go pre-processing again, modeling. But wait, you want to make more features, so you go back to feature engineering. So this process is very fluid. This is just a general pipeline to set like a groundwork, but this is a very fluid process that is not stringent at all. So when you're going through this, don't think that just because you're on the data exploration stage, you can't go back to you can't go back to the the context phase, or if you're on the feature engineering phase, you can't go back to the data exploration phase. Because you can always go wherever you need to in this pipeline. But these are all the these are all the things that you at least want to get done when you have a data science project. And then for next steps, you have deep learning, which is essentially neural networks. I actually recently gave a talk on deep learning that if you all are interested in it, I can definitely see if I can give another talk. And then natural language processing, which is taking text and turning that into your data. Taking raw text and turning that into data. It's extremely useful and for deriving a lot of features from very unstructured fields. Recommendation engines use it a lot. I believe Alexa uses it a lot. Alexa uses audio processing, but combined with natural language. But image preprocessing, like I said before, I kind of hinted at it. The Husky versus Wolf experiment, that was an image preprocessing one using convolutional neural networks and other advanced image processing techniques. That's a beast on its own. Basically, use pictures as your data, and then you make your models out of that. Audio preprocessing. Audio preprocessing is very similar to image preprocessing. Basically, you go through different steps to turn your audio into an image, and then use that image to create your model. And then reinforcement learning, self-driving cars is a very popular example of reinforcement learning. Maybe you want to make an agent to play a video game. Maybe you want to get a computer to play a video game, and so on. So yeah, these are that pretty much is everything I wanted to say. I had code, but it is already 5:30, so I won't get to go into it. But if you want to explore the code and see how all of these steps are executed in a code, I have an activity and multiple Jupyter notebooks that will definitely be shared at the end of this, so that you can dive further into it. Yep. Thank you so much for attending. I know I went a little bit over, but I love having such a fantastic audience who asked great questions. So it was it was very enjoyable to present here.
Yeah, and it was a pleasure having you, Alex. I know, and because of time, I don't think we're going to answer any additional questions. But I have taken a note of them, and we will see if maybe we can get a blog post going with some answers for you guys. So again, thank you, Alex. Everybody's saying thank you. Someone's giving you a standing ovation, so good for them.
Oh, thank you so much. Yeah, you guys were fantastic. The questions were so good. The questions were so good. We clearly have a lot of very, very smart people in the audience who very smart and attentive people. And I just couldn't be more grateful to speak for you all today.
Absolutely.